Chapter 2. 60. Look at a clock. Not a phone, an old-fashioned clock with a face and hands, or the memory of one. There are 60 seconds in its minute and 60 minutes in its hour. Turn from the clock to a compass or a protractor, or the readout of a ship's navigation system, and you will find a circle cut into 360 degrees, each degree into 60 minutes of arc, each of those into 60 seconds. When an astronomer gives the position of a distant galaxy, or a surveyor marks the corner of a property line, or your phone quietly reports where on Earth you are standing, the numbers come out in 60s. You are reading the arithmetic of a civilization that has been dust for 2,000 years. The people who chose 60 lived between the Tigris and the Euphrates. In the flat, hot country the Greeks would later call Mesopotamia, the land between the rivers, and which we now call Iraq. They built the first cities. They wrote the first laws and the first poems. And somewhere near the beginning of all that, for reasons they never wrote down, they built their counting on the number 60 and handed it, across 4,000 years and the wreck of every empire in between, to the watch on your wrist. Every hour you are keeping time in Babylon. We ended the last chapter watching number peel away from the things it counted, the moment 3 sheep and 3 days dissolved into plain 3. That happened here, in these river cities. And once it had happened, these people did something no one before them had managed. They started to calculate. Not to record what had happened, but to work out what must be true. Given this much grain and this many workers, how many days? Given a field of this shape, how much seed? They built the machinery to answer such questions by the thousand, and the heart of that machinery was the strange and brilliant decision to count in 60s. Why 60? It is a fair question, and the honest answer is that nobody is certain. But there are good guesses, and the best of them may be hiding in your own hands. Pick up the thread we left in Chapter 1. Hold out one hand and, with the thumb of that same hand, touch the bones of your 4 fingers. Not the fingers, the segments, the little sections between the knuckles. 3 to a finger, 4 fingers, 12. One hand counts to 12 on its own. Now, each time you fill up a 12, raise a finger on the other hand to remember it. 5 fingers over there, 12 on this side, 5 12s, and you have counted to 60 without a scrap of clay or a single written mark. Some scholars think this is exactly how it began. 2 hands, 2 different jobs, meeting at 60. There is a second reason, and it is the one a mathematician loves. 60 is generous. It breaks cleanly more ways than almost any small number you could choose. You can split 60 into halves, thirds, quarters, fifths, sixths, tenths, 12ths, 15ths, 20ths, 30ths. All whole, all tidy, no remainder. Compare that with 10, our own base, which divides evenly only in half and in fifths. Try to take a third of 10, and you fall immediately into the endless mess of 3.333. Third of 60 is a clean 20. For a civilization forever splitting harvests and inheritances and jugs of oil among 2 brothers or 3 creditors or 5 workmen, a number that shares itself out so willingly was not a curiosity. It was a gift. Whether the Babylonians chose 60 for that reason or simply inherited it and discovered its convenience later, we cannot say. Number systems are older than the records that describe them. 60 arrives already fully grown, its origins upstream of anything we can read. But the truly astonishing thing the Mesopotamians did was not choosing 60. It was inventing place. Here is what that means, and it is worth slowing down for, because you have used it every day of your life without once being amazed by it. Write the number 25. The 2 in it does not mean 2. It means 20, 2 tens, and it means 20 only because of where it sits. Move it one place to the left, write 250, and now that same 2 means 200. The symbol never changed. Its position changed, and position carried a value all its own. This is why we can write any number in the universe, however vast, with just 10 little signs. The digits do double duty. They tell you the count, and where they stand tells you the size. We call this place value, and we treat it as obvious. It is not obvious. It is one of the deepest inventions in human history, and for most of that history, almost nobody had it. The Egyptians did not have it. The Greeks did not have it. The Romans, who ran an empire on their engineering, never had it, which is why MCMXLVII takes 11 symbols to say what 1948 says in 4, and why you would not care to do long division with it. The Babylonians had it in base 60 before 2000 BCE. They managed it with just 2 marks, pressed into wet clay with the cut end of a reed. A thin vertical wedge stood for 1. A fatter, sideways, corner-shaped wedge stood for 10. To write any number up to 59, you simply group these, so many 10s, so many 1s, clustered together like the pips on a domino. And then, exactly as we shove our digits leftward into the 10s and 100s, they shoved their clusters leftward into the 60s and the 3600s. One position was 1s. The next position over was that same figure times 60. The next was times 60 again, times 3600. A little cluster of wedges meaning 2 slid 1 house to the left no longer meant 2. It meant 120. With this, the scribes could write and manipulate genuinely enormous numbers, and could multiply and divide with a fluency that would not be matched in Europe for 3,000 years. They kept tables, clay reference sheets, the ancient equivalent of the multiplication table taped inside a school desk, for products, for squares, for square roots, and above all for reciprocals. The numbers you multiply by in order to divide. Because 60 divides so many ways, most of these reciprocals came out clean, and division became a matter of looking up the right partner and multiplying. It was, for its age, a spectacularly powerful calculating engine. It had one flaw, and the flaw is instructive. The Babylonians, for most of their history, had no 0. Think about what a 0 is for. In 205, the 0 is not counting anything. There are no 10s. Its whole job is to hold the 10s place open, so the 2 and the 5 don't slide together into 25. It is a placeholder comma, a sign that says nothing goes here, but keep counting the columns anyway. Without it, you cannot tell 25 from 205 from 250, except by squinting at how much space the scribe left. And that is precisely the ambiguity the Babylonians lived with. A cluster of wedges meaning 2 might mean 2, or 120, or 7,200. Depending on an empty column, you simply had to infer. They coped the way we cope with a sentence like I saw her duck. From context, from the shape of the problem, from knowing roughly what size of answer to expect. Eventually, late in their history, they invented a little sign to wedge into the gaps in the middle of a number. But they never quite took the last step of treating that emptiness as a number in its own right, a thing you could add and subtract and reason about. That step, turning the hole in the middle of the counting into a number called 0, would be taken somewhere else much later in India, and it would take a chapter of its own. Hold the thought. For now, notice only this. The most sophisticated calculators of the ancient world built their entire system around a gap they could feel but never quite name. Now to the single most famous object these people left us, a broken piece of clay no bigger than a postcard, that has started arguments among mathematicians for the better part of a century. In the 1920s, an American publisher named George Plimpton bought it from a dealer for a modest sum, probably with little idea of what it was, and it eventually passed to Columbia University, where it is cataloged unromantically as item number 322 in the Plimpton collection. Plimpton 322. It dates to around 1800 BCE, which is to say it is roughly contemporary with the square root of 2 tablet from the last chapter. Old, in other words. Beyond easy imagining, older than Moses, older than the Trojan War, old enough that the pyramids were already ancient history when it was made. On its surface are 4 columns of numbers in 15 neat rows. The left edge is snapped off, so there were probably more columns once, lost forever. And the numbers that remain encode something that stopped the scholars who first understood it in their tracks. They are Pythagorean triples. You may remember the phrase from school, even if the details have gone soft. A Pythagorean triple is a trio of whole numbers that fit the sides of a right triangle. 3 numbers were the 2 smaller ones, each multiplied by itself and then added together, exactly equal the largest one multiplied by itself. The little one everyone meets first is 3, 4, 5, 9 plus 16 makes 25. There is 5, 12, 13. There is 8, 15, 17. They are rare, they are beautiful, and out in the wilderness of large numbers, they are very hard to find by luck. Plimpton 322 is full of them. Not the tame little ones, big ones. One row involves the triple 119, 120, 169. Another reaches into the thousands. These are not numbers you stumble across by trying triangles at random until something works. You would try for a lifetime. They were generated by some systematic procedure the scribe understood and we are still reconstructing. And the whole table appears to be ordered. The columns march up or down in a steady, deliberate progression, as though arranged along some smoothly changing quantity. What was it for? Here the fighting starts. Some have argued it as a kind of trigonometry table, 13 centuries before the Greeks supposedly invented trigonometry. A claim that made headlines around the world a few years ago and made a good many historians wince, because it dresses a Babylonian tablet in a costume sewn in ancient Greece. The most careful and persuasive reading, worked out by the historian Eleanor Robson, is less flashy and more human. It is a teacher's document. A tool from a scribal school for setting and checking problems about rectangles and their diagonals, the ancient equivalent of the answer key, at the back of the textbook. Generated so a tired instructor would not have to invent fresh right triangle problems from scratch every term. That reading matters because it lands us on the real point of this whole chapter, and I want to state it plainly. Whatever Plimpton 322 is, it proves that these people knew well enough to build a reference table around it. The relationship we now call the Pythagorean theorem. 1,000 years and more before a Greek named Pythagoras was given the credit. They had the fact. They used the fact. They generated it, tabulated it, taught it. And nowhere, not on this tablet, not on any of the thousands of others we have dug out of the sand, did anyone ever prove it? Or even state it as a general truth. There is no line anywhere in the Babylonian record that says, in effect, for every right triangle whatsoever, the square on the longest side equals the sum of the squares on the other two. There are only examples. Case after case after case, each with its own specific numbers, each one worked and correct, and the general law that ties them all together left forever unspoken, floating just above the clay, obvious to us and apparently invisible to them. They had the phenomenon and skipped the why. Now cross the desert, southwest, to the other great river civilization of the ancient world, and to a mathematics with an utterly different flavor. Egypt sat on the Nile the way Mesopotamia sat on the Tigris and Euphrates, but the Nile is a gentler and more punctual river. Once a year, with a regularity you could nearly set a calendar by, it flooded, drowning the fields under rich black silt in. Then, as it withdrew, leaving the land renewed and every boundary marker, every property line, every farmer's claim erased under a fresh blank sheet of mud. Someone had to redraw those lines. Every single year. The Greeks, looking back, thought this was where the whole idea of geometry had come from. Geometria, literally earth measuring, the art of laying the land back out again after the water had smoothed it clean. The men who did the laying out were called, in Greek, the harpodonapte, the rope stretchers. They walked the flooded fields with knotted cords, and by pulling those cords taut between pegs they reconstructed the rectangles of the world. Tomb paintings show them at it. A line of officials holding a long rope strung with regular knots, measuring a field of grain. There is a famous story, you may have heard it, that they carried a rope tied into 12 equal lengths, and that by pegging it into a triangle of 3, 4, and 5, they could conjure a perfect right angle out of nothing but string, since 3, 4, 5 is the humblest Pythagorean triple of all. It is a lovely story, and I have to be honest with you. We are not sure it is true. It gets repeated everywhere, but no Egyptian document actually shows them using the 3, 4, 5 rope, and some historians think it is a guess that hardened into a fact through sheer retelling. That the rope stretchers existed, we know. That they laid out right angles, we know. Exactly how they did it, the papyri do not say. File it, like the Ishango bone, under probably, but be careful. And notice, again, how much of the deep past is like this. A clear silhouette and a blur where the details should be. What we do have from Egypt is written down, and it is wonderful. The great source is a scroll called the Rhind Papyrus, after the Scottish collector who bought it in a market in Luxor in the 1850s. It was copied out around 1550 BCE by a scribe named Ames, one of the very few working mathematicians of the ancient world whose actual name we possess. And Ames tells us he was himself copying from a document 2 or 3 centuries older still. It opens not with a dry sum, but with a boast, a piece of advertising copy across 4,000 years. This, it promises, is the way into the knowledge of all things, every mystery, every secret. Then it settles down and delivers 80-odd problems about bread and beer and the slopes of pyramids. The Egyptians counted in tens, like us, but without place value, the invention that made the Babylonians so formidable. Instead, they had a separate picture for each size. A stroke for 1, a bent heel shape for 10, a coil of rope for 100, a lotus flower for 1,000, on up to a little kneeling god, arms flung wide, for 1,000,000. To write a number, you simply drew enough of each, 3 lotuses for 3,000. It is the same additive idea as Roman numerals, and it works, and it is clumsy for exactly the reason Roman numerals are clumsy. There is no easy machinery of columns to calculate with. And then there is the single strangest, most beautiful quirk in all of Egyptian mathematics, the way they handled fractions. We would write 3/4 as 3/4 without a second thought. An Egyptian scribe could not and would not. With one lonely exception, a special symbol reserved for 2/3, the Egyptians allowed themselves only fractions with a 1 on top. 1/2, 1/3, 1/4, 1/5, these were legal. 2/5 was not. Every other fraction in the world had to be built up as a sum of these unit fractions. And, this is the strict part, you were never allowed to repeat one. So 3/4 became 1/2 plus 1/4. 2/5 became 1/3 plus 1/15. 2/7 became 1/4 plus 1/28. The scribes even kept a reference table, right there in the Rhind Papyrus, working out the tricky cases in advance. A long list telling you how to break 2 divided by each odd number into a tidy sum of distinct unit parts. So you would not have to puzzle it out mid-calculation. Why on earth would anyone build their fractions this way? We genuinely do not fully know, and that uncertainty is itself a kind of lesson. It was clearly deliberate, clearly stable, they did it for thousands of years. And it has real advantages if what you mostly do is divide loaves of bread among workmen. If you have 7 loaves to split among 10 men, 7/10 of a loaf each is a number. But 1/2 plus 1/5 is a set of actions. Cut every loaf in half, hand each man a half. Then quarter the 2 loaves left over into fifths, and every man can see, physically, that he got his fair share, and no one was cheated. Their fractions were not really numbers so much as recipes for cutting, which tells you something about what these people wanted mathematics to be. They wanted it to work. And it did. It aligned the pyramids to the compass points with an accuracy that still provokes disbelief. It tracked the slope of a pyramid's face through a measure called the seat, so precisely that modern surveyors can read the intended angle straight off the papyrus. One document, the Moscow Papyrus, even contains the correct rule for the volume of a truncated pyramid, a pyramid with its top sliced off, a genuinely awkward shape. A formula so far ahead of its apparent context that scholars have puzzled for a century over how anyone could have found it. There is no derivation on the papyrus. No argument. Just the recipe, applied to specific numbers, coming out exactly right, with the reasoning that must lie behind and nowhere to be seen. Which is, of course, precisely the pattern we found in Babylon. So step back and look at these 2 civilizations together, the sexagesimal calculators of the rivers and the rope stretchers of the Nile. Because between them, they show us what mathematics looked like for the first several thousand years of its written life. And it did not look like what came after. It was a mathematics of recipes. I've worked examples. Open any of these ancient documents and you find over and over the same shape. Here is a problem with these particular numbers. Do this, then this, then this, and here is the answer. A quantity added to its own 7th comes to 19, find the quantity. A field of such and such dimensions, find its area. The problem is always specific, dressed in real barley and real workmen and real cattle. And the method is demonstrated by carrying it out, rather than by being stated as a rule. The student learned the way an apprentice learns a trade, by watching the master do it, then doing it himself 100 times, until his hands knew the moves. It was mathematics as craft, inherited, practiced, reliable, and taught by imitation. And it was magnificent. Do not let anyone tell you these people were simple. They built cities and pyramids and irrigation systems and legal codes. They computed with a speed and range, that shames most modern adults turn loose without a calculator. They knew the square root of 2 to a precision an engineer would sign off on, and Pythagorean triples that would take you a month to find by hand. Whatever they were not stupid, and the flatness of their mathematics was not a failure of intelligence. It was a difference in what they thought mathematics was for. For them, it was a tool, like a plow or a potter's wheel, something that does a job. And you do not ask a plow to justify itself. You ask it to turn the soil. But a mathematics of recipes, however brilliant, has a ceiling. And the ceiling is exactly the thing this whole book is about. A recipe can be spectacularly accurate and still be blind. It can tell you what happens. It can never tell you what must happen or what cannot. And so it cannot warn you. Come back one last time to that little tablet from chapter 1. The one with the diagonal of the square measured out to 6 sexagesimal places. Those beautiful, useless or once digits. Closer and closer and never quite arriving. The scribe who made it had a recipe that spat out better and better values for that length. On and on for as long as anyone cared to turn the crank. What no recipe on earth could have told him is that the crank turns forever. That there is no last digit. That the number he was chasing cannot, even in principle, be caught in pinned to a ratio of whole numbers. And that this is not a limit of his patience or his clay, but a fact welded into the bones of arithmetic itself. To know a thing like that, you cannot calculate. You have to prove. And in a scatter of windy trading towns across the Aegean, among people who bought their numbers secondhand from these very civilizations, and then asked of them, a question no Egyptian or Babylonian scribe had ever thought to ask. The question why, someone was about to invent proof. The first thing proof would do, almost as soon as it drew breath, was walk up to that innocent diagonal and reveal the catastrophe hidden inside it. That is where we go next.